Hello everyone, today we're looking at exercise 1C, which is all about implied or maximal domains. So today we're learning how to find the implied domain of any function and its corresponding range. What you need to be able to do is recognize features that may restrict the domain, such as square roots and fractions. Use these features to find the restricted domain, and if known, be able to sketch the function to be able to the corresponding range as well. So you may have heard this term, the maximal domain. We know that the domain are all of the possible values of x, but not every function exists in for every real value. So if the domain of a function is not specified, then the domain is the largest subset of R for which the rule is defined. And so that's what we call an implied or a maximal domain. So sometimes the question is not going to tell you what the domain is, but not every function exists for all of R. So we need to figure out what that would be. So here are a few functions to show you some examples. So this is a square root function. You can see that this exists from 0 to infinity. The reason for that is that that is a square root, and when you take the square root of a number, it will not exist if it's a negative. So that's why we don't see any values in the negative region. This here is a hyperbola. So same idea, you can see that it exists for all real values except at this point here. And that is the point when x is equal to 0. So if this function is 1 on x, what we know is that we can't divide by 0. So that's why at this point we have an asymptote. It will not exist at that point. Another function is a circle. Now, obviously a circle, there's no asymptotes or being cut off or anything like that here, but it only exists from this particular value to this value here, and that's just because of the nature of the function. So again, even if I don't specify that the range or that the domain is not R, we can see that it does not exist for all x values, that there's a specific point where it starts and ends. So our job today is to be able to figure out what that maximal domain is. And basically these are the two key rules. So first of all, look out for any square roots. If the value under the square root, or just consider that the value under the square root needs to always be greater than or equal to 0. I'll add that into here, or equal to 0. And then also look out for fractions. So the denominator must not be equal to 0 in order for it to exist. So let's go through a few examples. Example 1 says find the implied domain and corresponding range for the functions with these particular rules. So we can see that this is a truncus, but the key thing here is to recognize that this is a fraction, and we know that the denominator cannot be equal to 0. So I'm going to take that denominator and I'm going to say that that is not allowed to be equal to 0. And I'm going to go ahead and solve for x now. So I'll take the square root of both sides. Sorry, my pen sometimes goes a bit crazy. All right, square root of 0 is just 0. And then I'll just take that 2 over. So x cannot equal to 2. We can see that if we did substitute 2 into here, 2 minus 2 will equal to 0, which will result in a denominator of 0, which means it does not exist. So that means that the implied domain, so x can be any value, any real value, except for 2, because that is where the asymptote is. Now it does also ask us for the range. In order to find the range, we do need to sketch this function. So we can very quickly sketch this truncus. We can see that the asymptote is going to be at x is equal to 2, and it'll look like this. There's been no upwards or downwards movement. So the range will be from 0 to infinity. Not including. All right, part B says the same thing, find the implied domain and the range for this. This now is the square root function. So you might just be able to look at that and sketch it straight away. I'm just trying to do it through using the rules that we spoke about. And we know that underneath the square root, it is not allowed to be less than 0. So we will say x plus 6 needs to always be greater than or equal to 0. So if we take that 6 over, that tells us that x needs to always be greater than -6. So our domain will be from -6 to infinity. Now, as always, to find the range, we can go ahead and sketch. So this is the square root that's been shifted over to the left by 6. There's no reflections or anything that's happened. So our range we can see is from 0 to infinity. All right, next example, we've got this function. Now, I'm not sure if you know what this function looks like, but we can go ahead and start sketching it, and we can see where we go from there. Let's firstly find the implied domain. So we know, again, underneath the square root needs to always be greater than or equal to 0. So I'm just going to go ahead and solve for x. Now, the thing is, doing this, I'm going to end up taking the square root, and you're going to get a really weird answer. So actually, what's going to happen here is you can't solve it just by hand. If you recognize this is a quadratic inequality, and in order to be able to solve quadratic inequalities, you need to be able to sketch it. So we're not going to be able to solve this algebraically. I'm going to go ahead and sketch this function, 4 minus x squared, and what I want is for that to be greater than or equal to 0. So that's just a quadratic that's been shifted 4 up, and it is also upside down. And what we want is for the y values to be greater than or equal to 0. So that's from this point to this point. Now, in order to find these two values, we can just make it equal to 0 to see where it intersects. So then that will be x equals plus minus 2. So what this tells us is that x is going to be valid. So the domain of x will be valid between -2 and 2. Only between these two values is this function greater than or equal to 0. This might give you a bit of a hint about what this function looks like. So the general form of this function is this, and you may recognize this as a semicircle. So if you don't know that, that's okay. Hopefully now you've been exposed to it. Make sure you put it in your summary book. But this is our general form for a semicircle, and we can see that the domain corresponds with that. So this semicircle lies along the x-axis like this, and it is going to exist between -2 and 2. Doesn't really look much like a circle. Let me try that again. And of course, because our radius in this case is 2, that means the y value will be to there. So our range is going to be from 0 to 2. Okay, so that's all about implied domains and ranges. We're just going to kind of start digging deeper into the types of different functions that exist as well. So we've spoken about the different types of functions in year 11, and one that we came across was a one-to-one function. That means each x value has one corresponding y value, and we know that we can test for that because it passes both the vertical and the horizontal line test. So that's a one-to-one function. We also know about hybrid functions. So this is where you have multiple functions, but the key thing is that the domains do not overlap. If they did overlap, then it would no longer be a function because remember, then it wouldn't pass the vertical line test. What we're going to be exposed to now, which is new, is this concept of even and odd functions. So an even function, this is the key definition of it. So f of negative x is equal to f of x. So the idea is that if you were to substitute in negative x into a function, you'd actually end up with what you originally started with. So an example of this is x squared. Whether I subbed in a negative or a positive number into the x, I will end up with what I started off with. These functions are what we call even. They are symmetrical, and in general, you can kind of figure it out just by seeing that all of the powers of the function are even. Now, odd functions are very similar in that key idea. This time, if you substitute in negative x, you'll get negative f of x, so the opposite of what I started off with. An example of that would be x cubed. So if I sub in a positive number, I'll just end up with x cubed. But if I subbed in a negative number, you'll see I'll get the negative version of what I started off with. So a quick way to be able to recognize this is that all the powers of the functions are odd. So we're going to just quickly go ahead and test for even and odd functions. So this is the properties that we just spoke about. Odd functions has the property that f of negative x is equal to negative of f of x. So if I were to sub in negative x into here, if it's odd, then I would expect that every term is going to be the negative version of itself. So let's see. So if I take negative x cubed, that's going to stay as negative x cubed, and then a negative and a negative is a positive. You can see that when I compare the signs to what we originally had, now I've got a negative before I had a positive. Now I have a positive before I had a negative. So everything is the opposite, therefore this is an odd function. So even functions have the property that if you substitute in negative x, it's equal to f of x, so the original function. So let's test that out. I'm going to substitute in negative x into here. Can't really do much with the negative one. Negative x squared, so anything squared will always be a positive, so that'll be x squared minus 1. So you can see that the function that I've ended up with is exactly the same as the original function that I started off with. And that is the definition of an even function. That's the end of this exercise. Enjoy.